Okay, hi everybody. So let me start. I want to start with a kind of ancient problem, which is not really going to seem to have anything to do with algebraic geometry at all. Oh, I wasn't going to. How should
You
I?
can put the mic on. It's great.
Okay. Oh, it's a rule. All right.
Recording won't pick up your voice.
Got it. I'm still live. Very good. All right. Just here. How's that sound good? Okay. So let's consider the following sort of old chestnut. How much space do you need to spin a needle? In other words, well, a needle is a unit line segment, which looks like that. And if you want to spin it, well, you can sort of easily imagine spinning it around in a circle and getting a circle with radius 1/2. And you can ask, is there a more efficient way to spin this needle that is using less area in the plane? It's kind of fun to sort of think about how you would do this. And it turns out that it's not actually that hard to improve on this. Actually, it's sort of a fun exercise sometimes when I talk about this. You can sort of imagine, oh, maybe if you sort of move the needle and turn it very slowly and trace out a kind of annulus, you can do better. It turns out that this actually has the same area as the circle, if you try to do it that way. But if you do it in a kind of deltoid region like this, you can actually get it substantially smaller. So this kind of sort of extremal plane geometry problem was very popular in the early part of the 20th century. And people thought about this and tried to figure out what the smallest amount of space you could use was. And I think there was the result, which I think most people find pretty surprising, I certainly do, is that there actually is no lower bound. You can actually rotate a needle in the plane. The limit is 0 in an arbitrarily small amount of plane measure. So this is the famous theorem of Besikovich. So Besikovich says, any amount of space is enough.
Please write large.
Okay. And in particular, I actually don't really want to talk about spinning in this talk. What is a necessary condition for a region allowing a spinning needle? Well, it certainly has to contain a unit line segment in every direction, right? Because you have to sort of pass through all the directions as you go. So the notion I really want to talk about that comes from this is, let's say, a Kakeya set is a subset, and there's no reason to restrict ourselves to the plane now. Let's just say Rn containing a line segment in every direction. What?
A unit line segment?
Unit line segment, yeah. And so what Besikovich showed, I don't think it matters, but we can say that if we want. I'm gonna stop talking about measure theory like so soon. Anyway. Anyway, what Besikovich showed is that there exists, and he constructed it, a Kakeya set with measure 0. So I guess that one is measurable. So it turns out, is this a kind of curiosity of early 20th century plane geometry, as it might seem? Not really. It turns out that actually, as understood, I think starting with the work of Charlie Pfefferman, that harmonic analysts care about this kind of thing a lot because weird sets like this are a very fertile source of counterexamples to things that you might expect about various questions about bounds and norms of restriction of operators on function spaces, et cetera, et cetera. So in particular, this looks bad. It looks like Kakeya sets can be pretty small. On the other hand, Kakeya sets are pretty big in the following sense. So here's the theorem of Davies. That a Kakeya set in R2 like the ones originally contemplated by Kakeya, has dimension, Hausdorff dimension, 2, which is full dimension. In other words, it can't be like a curve, well that's obvious, but it also can't be sort of some crazy fractal thing with dimension intermediate between 1 and 2. So the analysts have all kinds of notion of like big and small. So it's small in the sense of having, it can't be small in the sense of having 0 measure, but in some sense, it can't be any smaller than that. So the situation in R2 is very well understood, and the famous Kakeya conjecture, which remains like a major open question in harmonic analysis, is that this is also true in Rn. So conjecture a Kakeya set in Rn has dimension n. Okay, well, there's lots of reasons not to say any more about this. One is that it's not algebraic geometry. 2 is that I don't know that much about it. And 3 is that nobody really knows anything about it. So the direction I want to talk about is a suggestion of Tom Wolfe from 1999, which is that maybe there's something to be gained in understanding the mysteries of this problem by trying to understand discrete analogs, which is something we do a lot in analysis, right? So Wolfe, 1999, suggests the following finite field model of the Kakeya problem. What if instead of the real numbers, we think about a finite field? And so the question he asks is this. Let E be what you might call a Kakeya subset of n-dimensional space over a finite field instead of the real numbers. That is, a subset of fq to the n containing, now I don't have to say a unit line segment anymore, right? Now I can just say a line, which has finitely many points, containing a line in every direction. And then you want to know that, that this set is large. So the conjecture is that the size of E is bigger than some constant, which is allowed to depend on n, times q to the n. So n we should always think of as fixed, by the way. Nowhere in this talk we're going to like let n grow. Maybe it's 3, or like it is whatever it is. So people worked on this conjecture. Terry Tao and Gary Muckenhaupt worked on it, got some partial results, but it also basically seemed to be quite hard. But by the way, like the original Kakeya conjecture, it's easy in 2-dimensional space, and that's a fun exercise. But in general, it sort of sat there as another hard problem that people in this area worked on for quite some time. And so that's why it was kind of a giant surprise when, in 2008, Zev Dvir proved this theorem. Maybe it's not so surprising that he proved it. What's surprising is he proved it in about 2 pages, using an argument that I can essentially describe to you in about 1 or 2 blackboards. So I'm going to explain that to you now, what Dvir did. And he was a grad student, by the way, for all the grad students, in computer science, not math. I also should add that so we can all feel humble. Yeah. Yeah, so that was going to be something I was going to say later and hope that no one observes spontaneously. But yes, there's 2 ways to read this theorem of Dvir's. One way is, oh, this is awesome. We proved something analogous to the Kakeya conjecture. The other way, which I have to concede I think is the more correct way, is, oh, oops, we were wrong to think that this was analogous to the Kakeya conjecture. Right? Because there's a clear disanalogy here. This, well, let me state his theorem, and then the theorem is that that is true. So maybe I will say that now, since you brought it up. So yes, a Kakeya set in fq to the n has size at least some constant times q to the n. And as, wait, are you Eric? Is that right? Who? Okay, so as Eric observes, this is actually analogous to something that is not true over the real numbers. Because this is really like saying you have positive measure independent of q. So Okay, one thing I'm not going to talk about today, but maybe I'll just mention it. Sort of my favorite question in this area, which I encourage the algebraic geometers in the room to think about, is so question, what about FQ double brackets T or ZP instead of FQ? So this, I think, is probably the right intermediate case that's more like algebraic geometry, but also more like the real numbers, and that there's multiple scales. Things can be sort of at different distances from each other. So I'm completely not going to talk about this issue today, again, because I don't know anything about it yet, but I recommend it as an interesting problem. Okay, so how did Beer prove this? He argued as follows. Okay, so let's say we have E, a subset of affine space over FQ, of cardinality n, and let's say this is a lot less than q to the n. So he says, well, if I have n points in space, I can find some polynomial that vanishes on all of them, right? I can run a hypersurface through them. We know the dimension of degree d hypersurfaces is about d to the little n, and so just by dimension count, we can find a hypersurface x, the vanishing of some polynomial, of degree, roughly, n to the 1 over little n. And by the way, in this game, there's like lots of constants, and for the purposes of the talk, they're just all going to be set equal to 1 because they don't matter. So let's just call it n to the 1 over n. Containing E. But now let's think about these lines, right? I have a whole bunch of lines. So what this means is, so let's let L be a line such that, and now we have to be a little careful, because what do I mean when I say that the line is contained in E? As algebraic geometers, a line is a line. It's not a finite set. I mean the FQ rational points of that line. So let's be precise about this. So that the FQ rational points of this line are contained in E. Which is a finite set. Well, then they're certainly also contained in this hypersurface. So in particular, you have that the intersection of the line with the hypersurface has size at least q. Well, actually, equal to q, exactly. Like, what else could it be? So maybe I'll write that. But capital N to the 1 over n, the only thing I know about it is that it's a lot less than q. So now I have a hypersurface of degree strictly less than q, whose intersection with a line has q points, and so by Bezout, this hypersurface literally has to contain the line in the sense that we, algebraic geometers, mean, not this sense in which combinatorists mean it, right? So now we literally mean, in the sense of algebraic geometric containment, this line is contained in X. Well, what does that mean? Remember that there's a lot of lines for which this is true. So we can say, so X, this hypersurface, contains a line in every direction. Let's be sort of careful. What do I mean by every direction? The FQ rational directions are parameterized by Pn minus 1 FQ. So X intersect the hyperplane at infinity, and I suppose I started by, I mean natural projectivization, contains all points of Pn minus 1 FQ, but its degree is less than q, so this is impossible. I mean, unless it actually contained this hyperplane at infinity component, but then that would mean the leading term was 0. It would just mean I was wrong about its degree, and on and on. So this is impossible, because this intersection is a degree less than q hypersurface in Pn minus 1. So that's it. I guess I did it in 3 boards. So what's the natural reaction to this sort of startling, very fast proof of like a conjecture that had resisted a lot of attempts by a lot of smart people, I think if you're someone in this room, you say like, well, if you can prove that, and all you know is Bezier, what can you prove if you actually knew some algebraic geometry, right? I mean, it's very enticing if you're an algebraic geometer. So this really launches like a whole beautiful story involving a lot of people in which algebraic geometry has been applied in rather novel ways to knock off many interesting problems in extremal combinatorics. And I'm going to sort of try to tell that story, including some of my own work in this area, but not restricted to that now. So this is, let's talk about sort of the post-Dvir era. So I'll just mention a few papers. The way I originally got interested in this was by writing a paper with Terry. So myself, Richard Oberlin, and Terry Tao. The Kakeya conjecture is a special case of what's called the Kakeya maximal conjecture on the Kakeya restriction operator. So I'll just say we proved in 2010 the finite field analog of the related Kakeya maximal conjecture, which uses more algebraic geometry, but not so much more. Probably the most famous result in this area is the result of Guth and Katz, also from 2010. On the Erdős distance problem, another kind of old chestnut of combinatorial plane geometry, which says that given n points in R2, the number of distinct distances between pairs. So it's sort of fun to think about this for 1 second if you've never thought about it before. I mean, so there's n squared pairs of points, right? And if you put the points generically, those are going to give you n squared different numbers. But of course, you can imagine trying to arrange the points in some way so that a lot of those distances coincided. If you could be in any dimensional space, of course, you could just put them in a simplex and they would all coincide. But being in a low dimensional space like 2 puts a lot of constraints on you. And I guess if you sort of imagine trying to actually do this, you would probably pretty quickly come to the idea that it's a good idea to like put them in a square grid of size about root n by root n. And it turns out that gives you about n over root log n distances. That is conjectured by Erdős to be optimal, and this is what these guys prove, are all up to a factor of root log. So these guys, the number of distinct distances is at least, sorry, I wrote this incorrectly. Yeah, determine at least n over log n. I don't want to talk about this one either. I want to start by talking about a different theorem of Guth and Katz, which resolves a conjecture of Bourgain about incidences between points, lines, and planes in R3. So it's another paper of theirs from the same year. So, okay, so given a set S of points in R3, and a set of n squared lines such that, okay, ready? So we have each line contains n points of S, and no more than n lines are contained in any plane So what you want to know is how small can this set be? I mean, if the lines were like completely had nothing to do with each other, right, and they were completely missed each other, and there was no intersections between them, then there'd be n squared lines, and each one has n points, and there would be n cubed points. But you can imagine that if there was a lot of intersections between these lines and a lot of points which were on many of the lines at once, that number could go down a lot. You could sort of more efficiently get this configuration with fewer points. And indeed, one way you could do that is if all n squared lines were in a single plane. Then they would intersect a ton. But we rule that out, right, by saying not too many lines can coincide in one plane. And then the theorem is, which was, again, used to be a conjecture of Morgan, then up to a constant, the lines are disjoint. You actually get constant multiple of n cubed. So somehow, lots of lines piling up in the plane is sort of the only thing that can go wrong, and apart from that, these lines are sort of as good as disjointed. The total number of points can't go below n cubed. So, yeah.
Why did Morgan conjecture that? Is that again like a discrete analog of something that comes up in harmonic analysis?
So that's a good question. I think I don't actually know the answer to your question. I can speculate. I'm going to talk about this question over finite fields, and it has a nice. I mean, this is a question over R, so I think in some sense this is a real analog of a finite field analog of a question analysts care about. You have to keep on like jumping over the river from rock to rock. So I remember Nets Katz coming into Wisconsin talking about this, and the proof is very much in the spirit of Zeb's view. The first thing you do is write down some hypersurface that goes through, in this case, a surface that goes through all these points. And the argument looked very algebraic, so I asked him, like, well, why are you doing this over the real numbers? I mean, this is an algebraic argument. Like, doesn't it work over an arbitrary field? But there was a problem with that. The problem is that it's not true over an arbitrary field. So this is quite puzzling because the argument is completely algebraic. Let me explain what goes wrong, and then I'll tell you a theorem of myself and Marksy Havlicek about this. This is not true over a finite field. There are counterexamples, which in fact are very commonly encountered counterexamples to lots of things in extremely combinatorics. Over fp squared. So let me explain how their proof works, and then you'll see what goes wrong at the very end. I'll sort of say it in brief. So what goes wrong with Guth-Katz? So I'll summarize their proof partly just to sort of show you what kind of algebraic geometry goes into these things. Well, the first thing you do is, their sketch of their proof is, okay, you find a low degree surface. Oh yeah, sorry. Passing through S, right? So if you assume that S has size a lot less than n cubed, the surface has degree less than n. So I'll call this x. So degree x, if the size of S is sufficiently less than x cubed, then this degree can be made less than n. So x, this surface. Oh, sorry, I'm sketching Guth-Katz's proof. And then sort of when you see where it goes wrong, you'll sort of see how to make the counterexample. So sketch of Guth-Katz. So x contains n points on each line. So by Bezier, as before, it contains lots of lines. And what you can see is that under the hypotheses, we're trying to make a lot of these lines intersect a lot. So in particular, you can check that there would have to be a lot of, and lots of things like this. So what is this supposed to be a picture of? This is 3 lines meeting at a point, right? I mean, certainly you're going to have a lot of that if you have some configuration with lots of incidences between lines and points. This picture is supposed to be a picture of 3 lines which are not coplanar meeting at a point, although you probably can't tell that. But those are like that's like a non-planar singularity. It's like the x, y, z axes. Okay, well, if your surface contains lines like this, then your surface has to be singular at that central point, right? Because you've given yourself a 3-dimensional tangent space. So this is what Morgan calls a joint. But this means that x is singular there. And in fact, if you have a lot of joints along the line, you can show that x is singular along the whole line, and then by the bound in its degree, you can bound how much of this happens. So let's just say by control of how big the singular locus of x can be given its degree, you can control how many of these you have. The other thing that can go wrong is that you can have lots of these. Well, that looks exactly the same on the board, but these are 3 lines in a plane meeting at a point. And if your surface has this, if your surface contains 3 lines in a plane meeting at a point, what that means is that the tangent plane to the surface at that point, if it happens to be smooth, actually is a higher degree of tangency than generic. Right? So this means, 3 lines in a plane. So this means many points where tangent plane to x has higher than generic intersection with x. So this is like the surface analog of a flex point, right, where your tangent has higher degree. So here you're almost at the end. You show that you look at the sub-variety of the surface consisting of points, smooth points where the tangent plane has higher than expected intersection multiplicity, and that's a curve whose degree you can bound, and you show that it can't happen. Well, no, it's not but then you're like, well, not necessarily. The only exception is, of course, if your surface is actually a plane, then, of course, the tangent plane everywhere is the plane and has massive multiplicity, but that's what you rule out here. So then this is their argument. They say, like, somehow, once this locus is a curve, you can bound its degree, and if this locus is everything, then it's a plane. And there, at the very last step, is where this proof does not work in characteristic P. Because in characteristic P, weird things can happen. So now, here's the kicker. In characteristic P, you can have surfaces such that every point has too high intersection with tangent plane. So this is like, I'm sure everyone in this room did this Hartshorne exercise about the funny curve where every point is a flex point. So it's like that. But I mean, this is a phenomenon, and I had to go back and read Kleinman's papers from the 70s about this to learn about this. That this is sort of, you can really study varieties in characteristic P where the Gauss map is inseparable, or non-reflexive surfaces. And that's what goes wrong. You want to conclude something as a plane, but you can't, and indeed, the counterexample that the combinatorists knew is a surface of exactly this kind in 3 space. So I'll just say, we sort of work all this out. It's a result of myself and Marcy Havlicek, 2013, which, well, it basically says the same thing. Same statement, but with plane replaced by non-reflexive surface. I mean, you have to sort of check that everything else works. But in particular, you can show that such a surface has to have degree at least P, where P is the characteristic. So one appealing feature is that in particular, the original statement of Guth-Katz's holds word for word over FP, over the prime field. But as it happens, and you can write down further examples for this, not over any non-prime field. It's not just FP squared. It's very strange. It's true over any prime field and false over any finite field other than the prime fields. So a couple things about that. Sort of one, it's just interesting in that I think it has been hard for people to sort of grapple with the fact that some of these theorems are true over some fields and not over others, and it's an interesting question to understand what kind of arguments are there that distinguish, for instance, between different finite fields. So here is one. Another point is that I just think it sort of points to the idea that we are used to thinking about these questions as questions about, this kind of thing is sometimes called like a Wolff axiom, where you say there's not too much pileup of one kind of linear variety in another. I think it suggests that in characteristic P, one is going to have to sort of have a somewhat larger cast of enemies besides linear spaces. I mean, these kinds of surfaces and other non-reflexive varieties inevitably play a role. And maybe I'll just say one thing about this that will sort of, it'll be a guess and an answer to Arnold's question about like why one might come to this particular question. So I'm going to use the bottom half of this. So in particular, in particular of the in particular, so given, let's take this theorem over Fp, and let's take capital N equals P. So given P squared lines in Fp cubed, no P of them contained in a plane, the size of the union of all these lines is bounded above by some constant times Cp cubed. And if you look at this, this is actually a strengthening of what Dvir proves. Because of course, if you had P squared lines that represented the P squared different directions, then certainly no more than P of them could lie in a plane. But this is a weaker condition that gives you the same result. So another question that this opens up is just, what is the weakest sort of spread condition on lines? What's the weakest condition on a set of lines that guarantee that they are up to a constant disjoint, that their union has up to a constant as many points as just the sum of the number of points on each line? And I really don't know the answer to that question, even in 4 dimensions, but it suggests that somehow Dvir's theorem is not sharp in this sense. Yeah, Dan?
Can you spell out what you mean by the same statement holds?
Oh, so if you have, do I still have it on the board? I will literally write, so if you have, just for an arbitrary field, and then I replace plane with like non-reflexive surface. Let's see, basically a surface where at every point the tangent to that point hits it more than doubly. So I think it's slightly weaker than non-reflexive. So I think we called it in the paper a planar surface, but it basically means that this thing that cannot happen generically in characteristic 0 does happen. Okay. So I want to take the rest of the time to talk about the newest piece of work that I'm thinking about in this direction, which is a paper with Daniel Ehrman. And for this, I want to go back, because this is a generalization of Dvir in a different direction. So there we saw the kind of funny business of characteristic P algebraic geometry coming into play. Here we're going to see sort of a different aspect of algebraic geometry coming into play. So, so here is a generalization of finite field Kakeya conjecture, which I'm going to identify this as Furstenberg, because it's an analog again, have a conjecture that is actually extant in harmonic analysis that people care about, which is, I mean, Furstenberg doesn't care about finite fields, I don't think, but this is sort of the finite field version of his conjecture. And it says the following: what if instead of lines, we think about higher dimensional subspaces? So we say, suppose E, again, a subset of fq to the n, is such that there exists a k-plane in every direction. So now here these directions are not parameterized by the fq points of projective space, but by some Grassmannian. So I'll just remind you that here's what this set of directions looks like. So exists a k-plane v in every direction such that the intersection of this finite set with the k-plane is at least q to the c. So now there's a couple of parameters. There's what's this dimension of this planes we're intersecting with, and of course, if I made this q to the k, in other words, if I said it contains a k-plane in every direction, then it would certainly contain a line in every direction, and then it would be big. So I don't want to say that. So what can we say about such a set? And of course, the case where k equals 1 is what Dvir proved. I mean, what I said was the case k equals 1, c equals 1, but it's actually not hard to see that Dvir's proof works word for word for any c in k equals 1. So k equals 1, Dvir, and the theorem of myself and Daniel Ehrman from this year is that such a set has size at least some constant, depending on everything except q, times q to the cn over k. So when k equals c equals 1, that's what I just said. But this is the general case. So to tell you about how we prove this, and it's actually kind of a fun exercise to try to think about what you would do if you tried to sort of apply Dvir's method directly to this. And trust me, I tried for a long time. I don't think it works, but I mean, maybe, you would start to say, okay, so if I have intersection with two planes, maybe I want to find, instead of a hypersurface, like something of codimension 2 that goes through all the points. And then I think we're sort of in the zone of, are you going to talk about this, Brian? Okay, so we're going to be in the zone of what Brian's going to talk about tomorrow, like super fascinating questions, like how low a degree curve in 3 space can you put through an even set of points, et cetera, et cetera. Anyway, maybe Brian can figure out how to solve this problem that way, but I could not. So let me tell you what we do instead, and I'll start with a kind of piece of philosophy about what separates us from the harmonic analysts. I mean, the relevant question here is, of what is a set of points a special case? So if you ask an analyst, they'll say a set of points is an example of a function, namely the characteristic function of that set, right? So is a characteristic function. And if you actually probe into why do harmonic analysts care about the properties of weird subsets of Rn, it's not because they sort of care about measure theory, it's because they care about functions on Rn, which can sort of be approximated by like sums of characteristic functions and multiples and stuff like that, and that's a sort of very tractable case. So in general, the conjectures that they're interested in sort of are conjectures about operators on function spaces which apply to characteristic functions, give you these kind of extremal questions. But for us, a set of points is a zero-dimensional scheme. And it turns out that for this problem, this point of view actually seems to do better. So let me explain how this works. So I'll explain, so what do we really prove? Not this, but something more general. Alright, so I guess I'll use this one first. So theorem, and this is again, it's really the same paper. Let S inside affine space over FQ a zero-dimensional subscheme. And let C be a real number in the interval from 0 to k. Parentheses here. Suppose there exists a k-plane B in every direction in GR, K, and FQ, such that V intersect S is bigger than Q to C. But now, of course, by this, what do I mean? I mean the scheme theoretic intersection, right? I take my scheme, I restrict it to this linear space, and I get some scheme whose degree is bigger than Q to the C. And, well, same conclusion. Then the degree of S is bigger than Q to the C n over K. So, one advantage of this formulation is, first of all, it's more general, it applies to more stuff. Second of all, it's very clear that it's sharp because I can just stick a fat point at the origin. Right? I mean, here it is. Fat point of degree, let me get this right, I guess I want it to be Q to the C over K. So the degree of this scheme in n space is Q to the C n over K. And in every direction, there is a k-plane that intersects it. Well, I mean, we know which k-plane it is, right? It's the one through the origin. And it intersects it with degree Q to the C. Okay, so it's sharp. And of course, the other advantage is that I know how to prove it this way, and I don't know how to prove it in a purely combinatorial way. So,
Say that again, the example. So degree, you mean the...
degree is completely the wrong word. Sorry, let me say, it's
You mean that power of the maximum?
yeah, so mod, the maximal ideal. So, okay, so let me write it. I'm going to actually write it out. So spec k1 of x1 directs n, mod, this maximal ideal supported at the origin, to the q to the c over k. So it's that fat point. So it's a scheme supported at the origin, which is this power of the maximal ideal there. Okay. So let me show you sort of step one of the proof. It looks like this. Okay. Here's a set of points. Here's another set of points. Here's another set of points. Here's another set of points. Okay, these are supposed to be all the same, but shrinking. I'm not really a good enough chalk drawer to make them actually look the same. But I mean, if I start with a set of points, I can just start dilating towards 0. Okay, and let's suppose that this set of points has the property we're interested in. That, there's some k-plane in every direction, I'll just draw one of them, that contains q to the c points of this set. Well, I mean, it's kind of obvious that if this set has the property, so does its dilating, right? It's just I might have to move that plane towards the origin a little bit, and so on and so on. So, somehow it's clear that what we should do is, instead of thinking of these things, you should just think of the limit. See, the analysts cannot do this. But we can. So in the limit, you get some kind of thing supported at the origin. It may not be exactly that power of the maximal ideal, although generically it'll be pretty close to that. But it'll be something supported at the origin, which will still have the exact same property. And so you can immediately reduce this theorem to proving it for schemes which are punctual, which are supported at a single point. So by dilation, can reduce to the case where S is supported at a point. Do I have time? It always reminds me of something that Ravi Vakil told me when we were both graduate students, when he was wise already and I was not. It was when he was thinking about solving combinatorial problems by making arguments on moduli space of curves. Do you guys remember this? And he would always sort of take some problem that looked hard on MG and degenerate to the boundary. And I would say, like, God, that seems like really hard, like thinking about these kind of stable curves and like things that are not smooth. Like, I like smooth curves. And Ravi said, no, see, smooth curves are the hardest ones. The degenerate ones, you have to sort of learn something and like deal with the singularities, but they're actually like much easier. And that's true. So this is some of the deep facts that I learned from him. And somehow it seems kind of scary to go from like finite sets to some kind of crazy like non-reduced scheme. But once you sort of know what you're doing, it's actually like much easier to prove things at this level. So in particular, what's easier about this is that all the combinatorial difficulty in this original problem, or in this original problem, is, well, you have to do this soup over k-planes, over the parallel family of k-planes. I mean, there's some crazy configuration of k-planes or lines or whatever all over space. Here that all goes away. There's no soup. There's no max, because you're not wondering which k-plane is the one that has large intersection with my set. You know which one it was. It's the one at the origin. But you only know that in the limit. It's not until you get all the way to the limit that the difficulty goes away. So the big benefit here is you know which k-plane has large intersection with S. And this actually makes many of the combinatorial difficulties go away. Now it's not over yet. Let me show you. Now I told you I was going to tell you what we really proved, and it was this, but that's not what we really proved. Now I'll tell you what we really proved. Because after all, what's the deficit of this? It's somehow it's still about finite fields. So in some sense I'm okay with that, because I'm really a number theorist, but as an algebraic geometer, we want to prove a geometry theorem, right? We want to prove a theorem about schemes that's agnostic about what field you're over. So now let me state the real theorem of the paper, which implies that one. So theorem, let K, a field, and by the way, given my answer to Eric's question about working over like z sub p or even z mod p squared z, I wish K didn't have to be a field, but there's like a lot of difficulty I don't know how to deal with away from this case. So with some regret, we let K be a field. And S, in AN, a zero-dimensional subscheme, and you see the point is that here there's still some reference to the FQ rational points of the Grassmannian, and that's not, as good algebraic geometers, that's not what we want to do. We want to talk about the locus in the Grassmannian of directions in which there's like a high intersection plane. So you have to define some moduli space, so that's what we do. So let X sub mk upper S, it's going to be a closed subscheme of the Grassmannian, be the moduli space of M-rich k-planes for S. Then either, one of two cases, maybe I'll write it on the, because I know that Dan's about to tell me to write bigger again, so let me get a new board so I can do so. So here are the two cases. Either the generic k-plane has big intersection with S, that is bigger, oh, so M-rich, sorry, that means that the k-plane intersects it with degree at least M. Is all of the Grassmannian, but in this case, S has to be pretty big. Some unspecified constant times M to the M over K. Or B, the set of geometric points of this scheme is contained in a hypersurface of degree at most some other constant times the size of S divided by M. So okay, so I think in the interest of time, I will just ask you to believe that this implies this, that somehow once not all the planes hit, you can bound the degree of the hypersurface in which the rich planes lie, and that shows that it can't be all the FQ rational points over there. So this is the sort of theorem of sort of Kakeya or Furstenberg type, which has nothing to do with any field and has nothing to do with counting. It's just a theorem about the locus of directions of K-planes that can have high intersection with a zero-dimensional scheme. So this is somehow what we were going for, some statement which implies the desired combinatorial theorem, but is really a pure theorem of geometry. And so I'll just close in the last 5 minutes. I'll say two interesting things about how this works. One is that restricting to the dilation makes it incredibly easy to reduce to the case where n equals k minus 1, the hyperplane case. I mean, this is completely impossible unless you go to this limit, but once you do this, so point 1, so induction, if every v through 0, if every k-plane v through 0 has intersection with v bigger than, let's say, q to the cn over k, and you know the theorem for, instead of kn, k plus 1, then let w be a k plus 1 plane, okay? Well, what do I know about S intersect V? And apply theorem to S intersect W. Okay, well, here's a zero-dimensional subscheme of W, and for every k-plane in W, because I'm assuming the theorem in the hyperplane case, it contains at least this many points, and so that means that the size of S intersect W is bigger than q to the, all right, ready? This is now C, and now it's times, what a mess. Okay, I should have said q to the C here, and then you get q to the C times k plus 1 over k. And so every k-plane has at most this much intercept. Every k plus 1 plane has at least this much intersection. And then you just go up and up and up. And for this to work, you really need to know that it's the planes through 0, like the actual linear subspaces, not some translates of those. So first of all, the one reason that makes it much easier is that you have this easy induction. In the case of hyperplanes, it's much easier to handle geometrically. Finally, in some sense, when we actually prove this, what we do is we degenerate still more, right? Dilation is not the only thing you can do. So I'll just comment that the idea of the proof from this point, so idea of proof is reduce to the case where k equals n minus 1 by the induction above. And then our thing is already supported at 0, but now we're going to degenerate into what's called a Borel fixed ideal. So it's sort of the maximally degenerate kind of zero-dimensional scheme. So degenerate to a Borel fixed subscheme, which is essentially, it's even more precise than this, but it's this mod some kind of monomial ideal. So in the case of two-dimensional space, it would literally be like a partition diagram, where you're modding out by just monomials in x and y. So in some sense, the shape of the proof, and once you do this, it's quote, quote, just combinatorics, right? So I think the shape of the proof in the end, I find rather charming because it goes like this. You sort of start with combinatorics, but I would call it combinatorics with moduli. That is, you sort of have some set of points, but they can really move around in your space. It depends what field you're over. And then you somehow, because we are who we are, we turn it into algebraic geometry. by generalization, by sort of thinking of a finite set as a special case of a zero-dimensional scheme. But then by degeneration, we go back to combinatorics. But now, if you like, combinatorics without moduli, right? I mean, questions about like monomial ideals, or somehow it doesn't depend what field you're over, and like nothing is moving, so it's sort of pure combinatorics, or as I like to think of it, the kind of combinatorics that somebody like me has a chance of being able to do. Okay, so we're just at noon, so I'll stop there. Thank you guys so much. Well, so what happens is, okay, so what happens is, really what you have to keep track of is making sure that you're not everything. And that's preserved under degeneration. So once you're in a, so in fact what happens is, you show that you're not everything, and then once you're not everything, the equations for these, for this moduli space, it's basically just some kind of giganto determinant, right? I mean, it's, the question of how big is the degree of the intersection of this plane with your scheme is, you have some massive matrix, and you like look at the ideal generated by all of its minors. So basically, once you show that they're not all zero, you sort of have an upper bound for the degree, like staring you right in the face, because you have a very explicit description. So you're absolutely right that you don't, that bound on the degree is not coming from the degenerate thing. That's coming from the original thing once you know something is not zero.
So, so far you proved stuff about point incidences with linear subsets. What if you increased the degree? Could similar techniques work?
I think basically in every case we know, everything is exactly the same if you're in some bounded degree. So for instance, in the paper with Richard and Terry, the first paper I wrote on this stuff, one of the things we do is sort of every statement in De Vere about lines, we sort of replace it with like curve of bounded degree, and everything still works. The one caveat I would say is that I can imagine certain situations like the stuff I talked about in Guth-Kac where degree up to p may be okay, but maybe there's some funny business. I mean, it depends what kind of thing you're using. Somehow, I guess loosely speaking, I would say in the arguments that we use for these kinds of Kakeya type problems, there's like no differential geometry, and so there's no worries about this kind of weird differentials and characteristic p stuff. Whereas some of the arguments that are more differential in nature, like this argument of Morgan conjecture, and I think probably Erdős distance too, then I would worry more about saying arbitrary degree, and I would sort of worry more about weird characteristic p phenomena over time.
Is there anything we can do to replace the AN? I don't know, like maybe putting this on some hypersurface and having to contain the intersection of some hyperplane with the hypersurface?
That's a good question. Again, I'm going to say, like, probably. Like, I mean, there's a lot of things. Again, I think in this paper, in the 2010 paper, in the paper with Richard and Terry, yet another thing is we sort of do that and sort of have it be it takes place in some variety, and you take like a hypersurface of bounded degree. I mean, I don't want to say yes because I haven't thought about it, but I would say usually for these kinds of problems, the reason that we prove them for AN isn't anything special about AN so much as it's like, that's what analysts care about, so that's the form in which the problems come to us. Now, I will say that in me and Daniel's method for this particular problem, somehow we're using this like very convenient to describe like big locus of degenerations that are like very, I mean, it's very easy to just kind of say like, okay, we're going to dilate, which is maybe harder to do if you don't have like a massive GM action on your thing. So I don't know exactly how it would work, but my intuition is that it would be very surprising if sort of the exact same thing were true. Sure.
Yeah, so in case B, so how do you determine this special hypersurface low degree from the subscheme S?
Yeah, so this is a technical point. What happens is we were actually very depressed because we thought that this locus itself, we thought that the moduli space itself was going to be low degree, and then when we computed its degree, it was like very large, and we were like very sad because then the whole thing just wouldn't have worked. Or it would have had some content, but it wouldn't have proven the original counting theorem over FQ. So let me see if I can remember the exact words to say. What you can show is that every geometric point contained in it is contained to massively high degree. And in this circumstance, we're able to use that to show that it actually contains some massive power of that hypersurface. So if you sort of imagine, like, let's say somebody tells you, I'm thinking of a hypersurface, and every single point on this hyperplane is contained in a degree of a billion, you could prove that it contains some power of that ideal corresponding to that hypersurface. So it's that hyperplane. So it's kind of like that.
Any other questions? Any announcements? Okay, let's join the